Hello students, welcome to Engineering Mechanics Statics. I'm Dr. Stewart and I will be recording these lectures which you will watch for the remaining of the semester. So let's go ahead and get right to it. Today's lecture is on Chapter 1. In this chapter we're going to go over what are the basics, basically what is statics, what are the basic quantities that are used, and how do we idealize problems of statics. What are Newton's laws of motion and how do they apply in problems of statics? And what are basic units? So statics. Statics is along the branch of basic mechanics. Mechanics is a branch of physics concerned with the behavior of physical bodies that are subject to either force or displacement. Mechanics can be subdivided into three smaller categories or three subcategories, which is rigid bodies, deformable bodies, and fluids. Statics is really the first in a series of courses that you'll have to take in terms of engineering. Statics can be considered the first course that connects mathematics, general physics with engineering principles. So mechanics under rigid bodies consists of statics, which are static bodies, and dynamics, which are accelerating bodies. Followed by that, there's deformable bodies, which are problems such as thermodynamics, solid mechanics, and the mechanics of materials. And then, later on, there is fluids, which is aerodynamics and fluid dynamics. Many of these courses you will be required to take along your course history here at UTEP, but we're starting here with statics. So, what is statics, and what is it? What is the problems that we will try to solve in statics? Statics is the study of rigid bodies at rest or at a constant velocity. It's concerning the determination of the internal and external forces acting on a body. So when we think about statics, we're thinking about bodies that do not accelerate, bodies with zero acceleration, that either have a constant velocity or have no velocity. When we think of statics, we can think of things that are relatively insensitive to time, or things that in normal use are insensitive to time. So house is a static structure, or bridge. You can consider a static structure, even though there are dynamic things that happen to them. And statics is concerned with determining the internal and external forces that act on a body. So if we were to apply an external force to a bridge, what type of internal forces inside of that bridge will develop? Or if we were to, apply some force to a wrench at the end of the wrench, what type of forces will develop at the bolt? So these are some of the kind of basic concepts that we would use in statics. So let's kind of go over a historical context for what is kind of the origin of statics, which is the first really engineering course that you guys will be taking. If we want to think of the historical context, then we really have to go back to the origin of mathematics. In terms of Western civilization, we can trace back the origin of mathematics to about 3000 BC. Civilizations such as the Egyptians and Babylonians, the knowledge that they developed was translated or transferred to Greek civilizations, which led to the development of basic Western sciences, and eventually translated into our modern interpretation of science, of engineering, mathematics, physics, and things of that nature. If we take a particular examination of just Egypt, according to Herodotus, the mathematics of Egypt had roots in surveying. The pharaoh gave each Egyptian, of course the upper class Egyptian, a plot of land along the Nile that would be taxed. And these Egyptians were the great farmers along the Nile. During the annual flooding of the Nile, due to the displacement of silt, so the displacement of land from one point to another point along the Nile River, it would require that a survey, a reassessment of the volume of land that the plot of land an Egyptian had, be performed so that the pharaoh could reassess taxes. So for Egypt, it started with the surveying or taxing issue, led to mathematics, trigonometry, and eventually a lot of this knowledge, this basic knowledge of mathematics and physics, translated into the architecture of these civilizations. So things such as their temples, the pyramids, things that we're still yet to understand how were actually engineered or actually built, considering how long ago this stuff was that they were made. And there's many archaeologists who debate on what method they used. Did they use pulleys or levers, basic engineering tools? But that's the one of the origins, or the classic origin of mathematics, leading mathematics, physics to engineering. A number of other civilizations developed or are considered to have developed mathematics and all the way up to statics, engineering principles independently. Naturally, there is consideration at the Asian cultures. Ancient China, developed many mathematic principles, trigonometry, trig, and architectural, basic architecture, independently from other civilizations. However, there is some debate upon that, but many Mesoamerican cultures in Central America and South America, including the Mayans, Aztecs, and the Olmecs, are considered to have independently developed mathematics and engineering principles. So in terms of the Mayans, about 2000 BC, Mayans and their fascination with astrology through religion developed mathematics in order to study the stars and in order to stargaze. Their development and understanding of this allowed them to develop their own calendar, and also led to them designing certain architecture, certain structures, in order to observe astronomical phenomena. So the buildings that were designed such they line up during an equinox or special solar days. So it's very interesting to see how different cultures have taken math and taken basic physics and led to some engineering principles and things, objects. So with that historical context behind us, let's go ahead and go into some of the fundamental concepts. The most basic fundamental concepts are the basic quantities that we use, that we will use in statics. There are four basic quantities that we'll use. One of them is length. Length is used to locate a body in space or describe the size of a body. So if an object is a certain distance from us, we can say it's a certain length. I'm standing here, and 4 feet from me is a table and things of that nature. It's 4 feet away from me in the X direction. It's 4 feet away from me in the Y direction. We can describe a location vector of where an object is in space. But we can also use length to describe the size of a body. So if we were to take a number of measurements, we can measure the length, the width, and the height of an object, and we could describe it in terms of length, in terms of area, or in terms of volume. So these quantities that build upon that the individual lengths that are measured. Another basic quantity is time. Time is conceived as a succession of events. So time is linear from a starting point, and each event follows in succession. In terms of statics, in general, we don't deal with issues of time, because statics, we're considering structures that are statically loaded. So there is an instantaneous application of force, which produces instantaneous response in the material. It's really independent of time, statics problems. Later on, later on when you take dynamics, you will be more concerned with time, and time will be a major issue. Another quantity is mass. Mass is a measure of a quantity of matter that is used to compare the action of one body with another. So these are quantities of matter And mass is something that we can use to compare how those quantities interact in various ways. And the final quantity that we can use is the quantity of force, which is considered a push or a pull exerted by one body on another body. So how objects interact in terms of each other is a quantity. So let's go ahead and look at the basic units for these four quantities. There are two types of units that we can consider. There are SI units, which are the international system of units which are used all around the world. And then there is US customary units, which are units that are primarily used in the United States and maybe 2 or 3 other countries in the world. And these two unit systems are very different. And it requires, for many of the quantities, well, for most of the quantities, a conversion factor be used to convert from one quantity to the other. To convert from one quantity's units to another type of units. So let's look at SI, which is the international standard, international system of units. In terms of length is measured in meters, which is denoted by an M. Time is in seconds, which is denoted by an S. Mass is in kilograms, which is denoted by a capital Kg. And force is denoted by newtons, where newtons is N. And newtons is equal to kilograms times meters divided by seconds squared. In terms of US customary units, length is described as feet, which is FT. Time in seconds, which is S. Mass as slugs, where slugs are equal to pounds times seconds squared divided by feet. And then force is equal to pounds, which is pound force. Now notice the difference between SI and US units in the way that mass and force is considered, where for SI units, newtons are a collection of variables, and how for US units, slugs are a collection of variables. This is a very important distinction, and this collection of variables can be useful in verifying that your solutions are correct. And this is something that there's a section in chapter 1 that you should definitely read concerning this issue of verifying the homogeneity of your units. Okay, now the next step is idealization. So in statics, generally statics is the study of physical objects in the world. Now when we think of physical objects, there are a number of real-world considerations that make applying basic statics theories problematic. So for instance, a large truss bridge has a number of physical features which are difficult for us to accurately describe using or to describe using basic statics. So we've got to simplify the problem so that we can use the application of some basic statics theory. So an example could be taking a soccer ball and say that soccer ball is in space and it's given an initial, a force is applied to it. We could take that soccer ball, which has a size, has like a volume, a size, and we can simplify it as a particle that has mass but no size. Because the situation that soccer ball is in terms of being in space, where size is not necessarily an issue, there's nothing that's going to necessarily collide with it. We could describe it as a particle that has a acceleration or has a velocity within some space. Another way to idealize something is a rigid body. So say we consider a span of a bridge or a piece of railroad that is a span of a bridge is probably a better analogy. Instead of taking that continuous bridge with continuous structure, we can turn it into discrete elements. So we can determine it into individual points that are connected by lines. And individual points that are connected by lines. And we can consider that this is something that has mass as well as size. And a rigid body would be described as a group of particles at a fixed distance from each other, which results in an object having size. Another example of an idealization is a concentrated force. Now, this is a good example in terms of something like railroad ties. A railroad. So say you have a train and the train's wheels are on the train track. So we have a wheel and it's in contact with this flat surface, which is a train track. We can take the load or the weight of the train and we can idealize it as a concentrated force at the point where the wheel comes into contact with the actual railroad. And so a concentrated force is a load acting at a point on a body. All of these idealizations allow us to more easily apply basic static principles and statics theories and get fairly accurate solutions of physical phenomena. So now that we've done that, let's go ahead and discuss Newton's 3 laws of motion. You should have seen this in your high school physics, or in physics if you've taken physics before taking this class. But let's go back over Newton's 3 laws of motion. Newton was really a luminary, one of the great polymaths of all time. Polymath meaning a great mathematician, physicist, engineer, one of the great scientists of all time. And his most significant contribution was to the field of statics and dynamics, the basic equations of motion, which we've used to design so many things in this world. Sir Isaac Newton was active from 1642 to 1727, and we'll go ahead and go in and describe his first law of motion. Newton's first law of motion states a particle at rest or moving with a constant velocity tends to remain in this state provided the particle is not subject to an unbalanced force. So consider we have some particle in space and we apply 3 loads to that object. But these loads and their configuration and magnitude are in equilibrium. So they balance each other out in every direction. And say this particle has an initial velocity, some constant velocity. Then if these forces are balanced and this body has some velocity, or it has a 0 velocity, it doesn't matter, then we can say that the sum of the forces, since they're balanced, is equal to 0. And this is one of the basic principles that we will be using. This first law of motion is what we will be using in statics. Now let's go on to the second law of motion. The second law of motion states a particle acted upon by an unbalanced force experiences an acceleration that has the same direction as the force and a magnitude that is directly proportional to the force. So what does this state? This states that if we're given some particle, we apply a force to it. That force that is applied to it will create an acceleration that is in the same direction. So the object, if you apply a force to it, it's going to move in the same direction and will have a magnitude that is directly proportional to the force. And this leads to the evolution of that basic principle, which is if the sum of our forces are unbalanced, then we will have an equation that states force is equal to mass times acceleration. There's a relationship between the force that's applied and acceleration that develops. Now, of course, if we apply multiple forces to an object and they are still unbalanced, then we can say that this equation is that the sum of the forces of the sum of the unbalanced forces is equal to mass times acceleration. This equation, the second law, is an equation that you will use in the dynamics class, where you have objects that are subject to some acceleration. But this equation will not be used in our statics class. Now, let's look at the third law of motion. Newton's third law states the mutual force of action and reaction between two particles are equal, opposite, and collinear. And this law is true if these objects are, if the forces of these objects are in equilibrium. So say we have two particles or two objects, they're each given a force, and we're assuming an equilibrium state, then the force of action and reaction between these two is going to be equal, so that we have equilibrium. They're going to be opposite, so that they cancel each other out, and that'll result in our sum of the forces equaling to force A minus force B equal to 0. And this third law is a law that we will use in statics. It's a little more detailed information compared to Newton's first law. So you will see the first and the third law in this class. Now let's look at the final principle that we will I'll discuss, and the rest you'll read in the actual book. The final principle we have here is weight. Weight is the force exerted on an object with mass due to Earth's gravity. Now remember, force is described as the push or pull on an object due to another object. So when we think of weight, weight is the interaction between an object that has mass with the mass of the Earth. So two objects with mass. Now, in general, we can take the equation force is equal to mass times acceleration, which is for force is equal to some mass times acceleration, and we can rewrite it as weight is equal to mass times the acceleration, or the gravity, the value of gravity. Well, gravity, the acceleration for gravity due to Earth is 9.81 meters per second squared in SI units, or 32.2 feet per second squared. Now, we will use this weight equation from time to time in problems in statics. And often we'll use this weight equation if we're given a mass. So if a problem says this object has some mass, then you can assume that you must calculate the weight of that object, which is a force which you'll use in solving a problem. So in general, these are the basic principles that I'd like to cover with you guys today. Hopefully these videos, I'll try to be as brief as possible so you're not stuck watching very long videos. But you definitely will need to watch these videos and be prepared for quizzes and in-class exercises. So what I'd like you guys to do after you've watched this video, or even while you're watching this video, is to read Chapter 1 and review the various components within Chapter 1. Chapter 1 is quite short, but in particular I'd like you to review units, significant figures, round off of numbers, and the calculations section. These are very important components that are better described through reading the book and doing a couple of exercises that are available at the end of the chapter. Again, my name is Dr. Stewart. I'm a professor in the Department of Mechanical Engineering at the University of Texas at El Paso. Thanks for your time.